Hope you're all having a good afternoon. And what better way to spend an afternoon than thinking about MEV? So yeah, let's make a start. So yeah, I'm sharing my screen. These notes, they're not actually available on a site anywhere. So that's why I've given you the PDF that's in the MEV channel. Yeah, so you've got everything that I'm going to go through. We are recording this as well, so we'll make that available and put that in the channel after we've finished. Okay. If you have any questions, yeah, pop those in the MEV channel. Okay. So Ron says not able to see the screen. So as far as I know, it comes out on there's kind of a pop-up on the right of your Discord. But, there we go. Okay. All right. Good. Now this, you should probably tell this is the first time we've tried this on Discord, so it may be a bit clunky. Apologies if it is, but I think we should be okay. And yeah, we've got the video as well, so you can watch that. You got the notes, so we should be all right. So this session it came out of one of the boot camps, and the Advanced Solidity boot camp. The idea that we were looking at opcodes and assembly, and I had this article that I thought was quite interesting, and I wanted really to be able to dig into that a little bit further. And so that's where this session came from, just the chance to have a dig into some articles a little bit in a little bit more depth, and the notes have sort of grown a little bit around that. So I've put a bit of background in the notes as well, just to give it a bit more context and to make sure people generally know what it's about. But really, the main part of it is meant to be about some kind of techniques some very low level techniques that we can use, and just to go through those. So let me show you. So we're going to start off with a quick review of MEV. So there's different aspects to this. I'll probably leave you just to read some of the notes for some of that as well. But that's where we're going to start with some background. Then also talk a little bit about the EVM and opcodes, because that's really at the heart of what we're going to be doing. Then we can make a start on the articles themselves and walk through those. And we're going to try out some of the code in the EVM playground, so we can see what's happening and see what it does to the stack. And then I've got a section about some optimization techniques. So I've tried to write a few more techniques as well that I thought would be interesting to look at. Okay. It's great if it's reasonably interactive, so please do put questions and comments in the chat. Yeah, and I'll get to those. But we'll start off with a quick review of MEV. The idea that this is value that can be extracted from the blockchain, but it has implications, and particularly what we're looking at today is the fact that people can do front running, and also we have the concept of arbitrage, and I'll come on to that in a second. But then alongside that, alongside really any kind of trading, I guess, that's happening on a public blockchain with a public mempool, we have the possibility that people can look at your transactions and then try to get ahead of you, and that can be a problem. The other point as well, and that where we kind of take it even further, is the fact that people write arbitrage bots or trading bots, and then the design of those and what they are doing obviously is, it has business value. And so we're also going to be looking at, the how you can sort of obfuscate what your code is doing to some extent, and actually also thinking about, is that a good idea to try to do that? Okay, so front running. Yeah, the idea is that we've got on something like Ethereum, we have a public mempool, so people can see transactions before they go into the block. so while they're pending. And that means that they can be cloned, so people can take your transaction and copy details from it. So if you've got there's some opportunity you're going to exploit, somebody else could spot what you're doing, get the details of that, then get their transaction in ahead of you. We have this idea of front-running bots, which is really what one of the articles is about, or is talking about what we can do with front-running bots or against them. Where front-running bots, what they do is they simulate your transaction locally, but they put their own address into the transaction instead of your address, and then they check to see whether they make a profit. So it could be that by putting in their own address, the transaction fails, or it doesn't make sense, or maybe it does nothing. But if they see that when they're simulating it, they make a profit, then they will go ahead, get that transaction, that modified transaction, submit it to the network, but put in a higher transaction fee so it gets ahead of your transaction, and therefore they steal the opportunity that you spotted. We also have, that's kind of general kind of front running. We also have very specific, some specific things as well called sandwich attacks. So with the front running, you can have back running where a transaction goes behind yours, and then the sandwich attack is where one transaction goes ahead of yours and one transaction goes behind. And there's a diagram here to show you how this could work. And we've got the example, this top transaction here. Our innocent user, he wants to swap some wrap teeth for USDC. He's going to do it on Uniswap, and he's specified an amount, some tolerance, the amount of slippage that he will tolerate. So if the price moves more than 1% against him, then the transaction will revert. What happens is, as soon as this is seen in the mempool, then a sandwich bot comes in. It works out that it can get a transaction ahead of this and move the price so that our innocent trader doesn't get as good a price as he was hoping. And then it gets a transaction behind his, which really closes out the position. So he sells some wrap teeth for USDC, and then he swaps that USDC back for wrap teeth. And you can see that this bot here makes 7 wrap teeth profit out of this, and it's just because by putting in trades he's able to move the price. The reason that he can make this, really what he's taking advantage of, is the knowledge that there is this large trade that's going into the network. So that's what allows him to make the profit. So we're always at risk of this kind of thing. The point about the slippage here, this gives a limit to how much the bot can move the price. So when he does his initial transaction, he moves the price, but it has to be within that 1% tolerance. Otherwise, our innocent traders' transaction would fail, and the whole thing would be pointless. All right. So that's sandwich attacks. There's an example here. This was something also in real life, which seemed to get triggered as some trades went in over a certain volume. Then that seemed to trigger the sandwich bots to come in and take some profit out of them. This link here shows you an overview of how much is happening at the moment, and what's being exploited. So these are the different contracts. So we've got like Uniswap V2, etc. And you can see the profit that is being taken for all of these. So it's not always a huge amount of profit. This is the kind of the breakdown of the different amounts. So there's lots between $0 and $10, and then not much out higher than that. But still, if you do a lot of these, then you'll, those small amounts add up. Okay. I hope you can. Were you able to see all of that? I hope. Yeah, I think you could. All right. So arbitrage. So this is kind of a separate thing, but they are related because if you're doing arbitrage, then obviously this is a type of trading. You need to be aware that people could also be trying to do a sandwich attack on you. The idea behind arbitrage is that there is two markets, two exchanges maybe, or exchanges on different chains, whatever it is. But there's the discrepancy in price, and arbitrage is all about taking advantage of that discrepancy. So you put in trades which will give you a profit by taking advantage of that. And this is useful for the market, for the ecosystem, because by doing that, that means that the prices will eventually align. These extra trades that the arbitrageurs bring in will align the prices across the ecosystem. These could be being done with indexers, or they could be sexers. It could be cross-chain. Yeah, many different sort of possibilities. Liquidity obviously is an important factor that you need to be aware of if you are doing arbitrage. So a few details here about this. You're probably aware of this already. But when if you are doing arbitrage, and whether that's manually or if you've automated it, maybe you've written an arbitrage bot, you do need to have things such as a calculator to work out what opportunity is there. So how much profit could there be made by taking advantage of a price difference? And then you also then need to take into account the costs of actually doing that. And part of the costs of that are going to be transaction fees, which is going to depend upon the amount of gas that you're using. Usually you're using a contract to do this, so there's going to be some gas involved with that. So if you can make your contract that is doing this more efficient, then that allows you to take advantage of more opportunities because you're lowering the costs there. Yeah, various details here. Probably don't need to go through it. It's a complex area. But what we're looking at really is, for example, some of the optimizations that you might want to do if you are trying to do this, and also how to, perhaps if you've got an arbitrage bot that's running or some trading bot and it has some clever algorithm in it, then perhaps you might want to hide details of that from other people who would want to steal your ideas. So yeah, this is all what we're going to be talking about. Yeah, few details there. This is really just background for you. I think you may already know this, but and then the general flow. Maybe you would look at a particular token pair, look at the prices across exchanges. If it's above a certain amount, then you provide a signal. Then you would execute arbitrage on that. Maybe you'd just automate part of it. So perhaps you would just have something that automatically looks for these opportunities and then lets you know, and then you go in manually to do the arbitrage, or maybe you automate the whole thing. But it does involve things such as gas costs, which is kind of what our focus is going to be today, and also this slippage as well. Okay. Yeah. So, question about the slippage percent. Yeah, I mean the point, or the trick, or the skill with this is that obviously if you allow too much tolerance and you allow too high a slippage, then you're opening yourself up to be exploited, and get a worse price. But also there may be some price changes anyway, and so if you put a very small slippage, then it could be that every transaction that you put in is going to revert, and there's still going to be costs to that. So you have to kind of find a balance there where you are actually managing to get trades through, but you're still getting reasonable prices. Yeah, that's a good point. All right. So let's take a look at these articles then. So there's 3 articles that we can have a look at. From the original one was, I think, the second one actually. The mempool obfuscation one from Digachi. He also wrote this one here, um, about how to build an MEV bot. We can quickly have a look at that as well. It's just really an overview. So things that he says. First of all, the sort of fairly obvious idea maybe, but if you're going to start doing this, then you'll need some kind of strategy involved. And how do you do that? Well, you could copy somebody else's, so you can work out what other people are doing. And again, this is part of the reason we might want to obfuscate the things that we are doing. If you are trying to work out what other people are doing, then there are sources of information. For example, you well, it's unlikely that people are going to be putting their source code out, so you're probably just going to have bytecode, but bytecode is going to be available, so you can look at bytecode, and obviously that's why we're looking at these obfuscation techniques. But also you can also work out by looking at the block explorer the types of things that are happening as well. You can no doubt work out things there. I mean, even that example I had earlier, the sandwich bot thing. I could just see from the way the transactions were going that there seemed to be a limit on the volume. Above a certain volume, then this sandwich bot seemed to kick in. So the block explorers can give you quite a lot of information. There's a lot they can do, so they're a very useful tool. But one point is, if you are copying someone else, that means you're both doing the same strategy. So you're then competing for the same opportunities, and what's going to decide who wins in this competition? Well, perhaps they're going to be, maybe they will adjust fees to try and get ahead of you, or maybe you can do that, try and get ahead of them. Or it could be that maybe they have a better connection, they can get to the network quicker than you, that kind of thing. So once, if you're using the same strategy, then it's going to be those types of things that will differentiate between you. If you are copying someone else, then they're probably fairly experienced. They've probably optimized what they're doing. But then again, so it may seem like a bad idea, but then it saves you doing all that work. So yeah, it's something you're going to have to decide. The other thing you could do, of course, then is to work out your own strategy. I think this is probably potential to make more, in the sense that you could help you stand out then from other people. But for that, obviously, you need a good strategy, and you're going to have to put more work into that and do more building to actually do that. Yeah. So yeah, this is the point here. You get highly rewarded to think out of the box. So that's that point. The details here. Yeah, he said, yeah. I don't know. The point here about using Rust, I'm not sure that's necessarily. I think other languages are perfectly reasonable as well. All languages get optimized, and they can be very fast. So, but yeah, Rust is a perfectly good language as well. You'll need monitoring as well to work out what's going to be done. Yeah, there's a few deals here. Probably don't want to go through this much more. If you're interested, though, yeah, do work through this article. But also be aware that a lot of other people will have read this article. So with a lot of these things, I mean, trading generally, it is competitive. You are trying to stand out from other people. So if you're doing exactly the same thing as other people, to the letter, then you're unlikely to beat them. So that's back to the thinking outside the box point we had earlier. So it's becomes a hardware competition. It's a different point, but I think that's true. All right. So anyway, you can have a look at that article. Lots of good stuff there. The next one, then, the one that really I was that sort of started this that I was really interested in was this one, and I wanted to dig into this much more because I think there's some interesting ideas here. So I wanted to work through them to give you chance as well to uh, get some experience at some of the techniques here as well. It's I think he was motivated by this because he was trying to defeat the generalized frontrunners. So he was trying to think of ways to do that, and this point here is that he's saying that the front runners are going to be going in and they're going to replace an address in the code with their own and then try to work out if there's a profit. So don't forget that if people are simulating things locally, for example, if you're using something like Tenderly, you you can you can take the bytecode and you can adjust it. You can take any of you can take source code and adjust it, and then rerun transactions against adjusted code, things like that. So, there's lots of potential for people to try things out and try to work out what you're doing. Okay. Now, in the notes, what I tried to write out some of the details of this as well. Sort of pick out some of the techniques that he was using. Yes, but let's. So this is really a sort of précis of what he's got in the article, but we can go through. No, let me close that one. We can go through what he's trying to do, or we can have a look and kind of work it out. So this initial one, what he's saying, is that what they can do is use code size or Xcode size to check whether this is a contract or not. So I think hopefully you understand that. I'll go to my I've got my EVM codes ready here. I recommend you have these ready as well. If you have a look at what code size is doing, so this is the way that we can look at the amount of the size of the bytecode for the current environment. More particularly, I think, though, this one, if you supply an address, then this will tell you the size of the bytecode for that address. And so what he's saying here is that this could be used to check whether the address is a contract or not, because then the bytecode will be greater than 0. That's not a foolproof technique, but that can work. So that's something that they might be doing. They may be trying that out to see whether something is a contract or not. They're trying to work out where they're trying to work out where they're going to replace the address within the bytecode for what you're doing. So they could just be looking for this within your bytecode. So what this is doing here is saying, look at the size of the bytecode. If that is 0, then jump and then you're going to stop. So this is testing for a contract. Okay. And the red dots here are what would happen if it isn't 0. So that's what that's about. Okay. But then apparently they're even more sneaky than that, and you get them looking for areas in the bytecode where you're doing a push onto the stack for which would be pushing an address. Okay, so that might be they might be doing a push 32 or a push 20, and when they see that, then they could try replacing that with their own address. So why don't we try some of this out? I don't know if did I? Whoops, I don't know. Give me a second. Oh, sorry. Try again. Okay. Now this, if you copy this, it comes out slightly wrong. You have to try and get it. I think that's okay. All right, so that worked. All right, so what? Let's work through what is going on here. So we've got a they're trying to it's trying to execute a function. So the first part here, we're doing this push for, which is the function selector, and then putting that. You can see we do that goes into the stack. We then do a push 0, puts a 0 on the stack. We do an M store. We do an M store here, and then that stores it in memory. And then, so you can see there, that's the function selector. We then do a push 20, which is pushing the address, and then we do we put a 4 in there and store it. So that's putting the address we have. So we've got the dead beef address. Excuse me. And then we're putting that in memory. So you can see that's now in memory as well. So the first piece of memory was just this, and then after that we've put all of this. Okay, hope that's clear. Yeah. Okay. And then we're putting some zeros on the stack. Yeah, so this is that. That's that. We then are looking for. We're looking to set up the function. So this is putting this on ready for call data. Where have I got? That is an address that we're going to be calling. And then we do the call, which is going to execute it. So let's have a look at that. Call. Okay, here we go. So the call, you can see, is quite complex. So we need these details on the stack, which is why we had to put all of this stuff there, because those are setting up all these things ready for the actual call, which we've got there, which is going to make our call. And I do that, and it's brought back a 1, which means success. Okay. So what did we put on there? So we had 3 zeros and a 2 0. So we had these were 0. This is the offset in memory where we are going to have the input, and then 0. Actually, this maybe it's the. Have I got this wrong way around? Because I think we have the gas, and the address. Yeah, sorry, I'm getting this the wrong way around. So we have the gas, the address. We have the offsets, where we want to send the inputs, and then where we want to get back the outputs. So that will all have be gone on there. That's the address of the contract we're calling, and then we call it and we get back a result. Okay. Is that okay? Did everybody follow what I was just doing? This is just he's saying this is just a standard way to call a function. So that's really all that we've just done. Okay. I mean, please do use your own playground. I'm just using evm.codes, using their playground to try things out, and you can see I'll get this on the stack, etc. Oh, someone's typing. He's very creative in his language. Unfortunately, I'm not so creative. So I just kind of stuck to the facts when I was giving a précis of the techniques. But though the techniques really are just what you see here. So we're moving on to the address shifting now. Yeah. Okay. So we've got this thing, the push 20, which is putting our address onto the stack. So somebody could go in, look at the bytecode, and say, well, push 20, that's a bit of a giveaway. Why would we move 20 bytes unless it was an address? It's only really going to be an address that is 20 bytes. And then, they could work out then that that's your address. So it's, definitely a bit of a giveaway, a giveaway. So what he's decided to do is to be a bit sneaky and try and obfuscate the address a bit. So see if I can show you that. So we've got our address, but now we've put something else on the end. And so when we're doing the push, we're not doing a push 20 anymore. So if you see that, then that's what you get on the stack instead. But obviously we need to be able to convert that. So we put the 8 on the stack, and then we can do a shift right, and then we get back our original address. So that's a very simple technique. So let me just move that out of the way. The gas must be on the top of the stack. We were having the address on top. Okay, maybe I got that wrong. Yes, it should. This is going to be correct. This is going to be the order. It should be gas. Did I have? I can't remember. Remember when you're putting onto the stack, you put the last thing on, and then you put the next thing on. It pushes the thing down. So the gas should have been. Let's go back to his code. Yeah. Oh yes, it should have been which way around? Yeah, it is. It does look the other way around, doesn't it? Yeah. Okay. Anyway, okay. Yeah. Looks like it should have been the address and then the guess. Okay. Anyway, so yeah. So one way we can disguise the fact that we've got an address is by adding some bytes to the end, and then we can do a shift right to take them off again. Okay. Yeah, so that makes sense. Other things we can do. are this. So where so this is what we split up the address basically in this one. So I think I've written it better. Yeah, so we split it into the smaller parts. So what we get then, we've now put it into two parts, as you can see here. We can put that onto the stack. We have to shift left initially, so that we've got this here, because we want that to be to be kind of space for the rest of the address. We then put the other half of the address on the stack, and we sorry, I didn't maybe that was too quick. Let me do it again. So we do that. We put the other half of the address on the stack. So this is the second half of the sorry, that's the second half of the address, and then we OR them together, and that gives us our original address. And we can put that into memory, just the bottom of memory, as you can see there. So that does disguise it further, because not only do we not have a push 20 now, but also we don't really have anything that looks like an address. Our address has been split up into two parts there. You can keep doing that, but do it into smaller parts. So here you can see we're splitting it up into different parts. So we've got this bit, so they don't have to be the same size, and this bit, and then depending on how big the parts are, you need to do different types of shifting. And this is putting some to memory as well, I guess. But at the end of it, then you should end up with a some of it in memory. Okay. So so this is another way to disguise what we're doing. Also, what you can do, you can take further this idea of the ORing that we had here, and work out what you can work out how to split up your address by ORing it as well. I mean, we did that initially, but what we did was we kind of had the original address, and then we put some zeros in and did an OR, and then that put them together. But this one is breaking it down even further. So you've got things that you wouldn't even know would relate it to this kind of dead beef just by looking at those. It's only by when you OR them together that they would make sense. So no, that's going to work, because hopefully, yeah, there you go. So we've got that part of address. We can split it up further by working out what would be needed, what bits are needed, and splitting it up like that. So that's another technique. Oh, and I think he just puts all of that together there. Yeah. Let's show it all. So yeah, so that was the bit we had before. This bit here then is where we used to have, where we had the dead beef, and we recreate that there with the XOR, and then we can store that like that. Okay. Other points he's got here. vanity addresses. So one point about this is, well, vanity addresses are used anyway because they are cheaper when we're manipulating them than any kind of random address. So that makes sense. But what I think what he's talking about here is that you create a vanity address with a particular number of zeros, and then it becomes even less obvious that this is an address, particularly when you combine this with the other things that he's done by, for example, putting zeros on the end. So that can make it even even less obvious what's going on. Um, Question: this obfuscation done by an MEV try not to be front run by other MEVs. Yeah, so yes, that's it. So it's it could be to prevent front running. Also, is to disguise really what he is doing. So if there's some bot that is taking looking at that contract and then saying, okay, I can see that here I know that there's an address being used here. So what I'm going to do is I'm going to put my address in that the transaction instead, or it could be in the contract instead. Is trying to get rid of that, trying to make it more difficult for someone who's trying to front run it, particularly as something like a generic front running bot that is just going through and trying to replace addresses and then work out if they can get a profit from doing that. So it's trying to make their life much harder. So it's trying to disguise where addresses are being used in the bytecode, so front running bots can't go in and replace them. Yeah, that's that. Okay, just wait for the next message before we go on to the next one. Does anybody get the idea, why the motivation behind this? Okay, I'll quickly go on to start talking about this. This is quite clever. I hadn't really, I haven't gone through this exactly. Well, no, I do get what this is doing. So, and I think this is quite clever. So let me try and explain it to you. So what uh, what he's trying to do again is to really obfuscate what's going on in the with the bytecode and the transaction. So if you imagine, that he's got a transaction into the mempool. Obviously, we know the bytecode that's associated with that transaction, but these front-running bots don't know what this transaction is about. They don't know what the bytecode is trying to do. What? Oh, I'm going to. Sorry, they don't know what the bytecode is trying to do, and so they're trying to look, for ways to abuse this transaction, abuse the bytecode. So what he's trying to do is to make it so they can't work out what's going on, and they'll leave that transaction alone. And so what he's doing here is uh, altering the flow of the transaction or of the execution, depending on who is the builder of the block that this transaction is going to be in. So if someone takes this code and they run it locally, then presumably the Coinbase here, the person who is going to get the block reward, who is the ignoring proposer builder separation, the person, the block proposer, they are, that would be a certain person on mainnet when it's actually happening for real. If you're doing it locally, then that's going to be something else. So what this would mean is that when this is running locally, it's probably not going to work in the same way as it is when it's running for real. I suppose maybe the generate front running bots would also, perhaps they're going to set the Coinbase to be the person who is going to be the block producer in, the for the next block. But maybe they'll do that. But otherwise, I think this is going to try to get around that. So, it's going to. Oh, I think I've tried to jump somewhere. Impossible. But it's trying to get. Try to jump around depending on the expected builder for this. Which get quite a clever technique. Okay. So the question: a more advanced bot could simulate the transaction to find the address. Well, no, that's the point. So this is what he's trying to stop. He knows that some bot is going to be simulating this, and so he's trying to make it more difficult for them to work out the address. So the bots generally will be getting these transactions. They can run a transaction, and obviously message sender will be their own address. So that's one thing that could be there. But they could also go further, because perhaps there's going to be some address within the contract that they could also switch out for their own address. And so what he's doing is trying to make sure that the addresses in the contract that they would be looking for to switch out are not obvious. So these are, he's saying they'll be looking for things like push 20, but a way to get around that is not to use push 20 with a normal address, but to use push 10 and split up your address and then recombine it later. So there's going to be a kind of an arms race between, somebody doing this and the front running bots, who would have to then put in extra techniques when they're doing the simulations to look for all this type of thing, which is going to be quite difficult for them, I guess. Okay, is Coinbase not a is that not an opcode? What did we? Nope, it is not code. Yeah, so that is something that could potentially change then, as the block is mined, and then the logic would change within something like this. Of course, to do this, then I'm not sure quite what he was. Perhaps he thinks he's going to, put in the addresses of all of the builders that are expected. But I suppose you can, maybe he could try and work that out, what the Coinbase is going to be, and then no, you'd have to put in a lot of addresses, I would have thought. Yeah, so I'm not sure how feasible this would be, but interesting idea anyway. Yeah. Okay. So what else does he say? Yeah, so I think, well, what do people think? I think those are some, really clever ideas, and it would be quite difficult for someone who's writing a front-running bot to, write things to get round all of these. And probably not worth their while. There's, rather than do that, then they're just going to go on to other transactions with people who haven't, got this kind of obfuscation going on. But it's quite clever, what he's done, I think. But yeah, I'm interested in your thoughts. Okay, nobody's got any thoughts. All right. Yeah, I guess okay. So that was that one. And I've written it all out in the notes as well. About that. Yeah, about the pending transactions. Okay, and then I'll just wait for comments. Actually, yeah, we've got a few comments. Good. I'll wait for those to come in and then we'll move on to the next bit. I wonder if I could work out. Oh, I was wondering if I could set up a poll, but I don't know how to on Discord. Okay. Is front running taken care of inherently on certain L1 or L2? Yeah, so on L2s it's a little bit different because they have sequencers and they're the ones who are deciding the order of things, and they could potentially you don't necessarily have a public mempool then, but the sequencer could front run you also. And then the other point is that there's other mitigations against front running, which are things which some protocols will have in play. Certain DeFi protocols work differently to try to avoid front running. Or of course, you've got the things like flashbots, etc. That is as a way to get in transactions going in privately and avoiding the public mempool. So yeah, this isn't the only way that you can avoid it, but it is one way to try to avoid the front running bots a little bit. Yeah, generic front running bots. So DeFi protocols, there's different ones doing things in different ways. I mean, the one I was thinking of, things like CowSwap, they work on intents where if you're thinking about doing a swap, where we had the example earlier where we had our innocent trader who was trying to do a swap and he got sandwiched. With CowSwap, what you can do is you can send in an intent to do a swap for a certain amount, and then that will get matched with somebody else who will kind of take the other side of that order. And there's it's trying to avoid the public mempool and things going publicly and then onto the exchange. It sort of organizes it outside that. Yeah. Is the TX simulator MEV bots used similar to the ones for is 4337 the is that account abstraction? Yeah. So I think that no, I think maybe that's a separate thing. I think transaction simulators, they're just tools. I mean, things like Tenderly that you can use, which will let you simulate things locally. Or I mean, you can write your own tools, of course, as well. Yeah. So title say makes sense for protocol try to obfuscate the transactions on chain. Yeah, so you do get that as well. Is it secret network where they uh, they do some encryption to try to stop it being obvious. Um, yeah. So okay. All right. Now this next piece. This is going a little bit simpler. I put together some examples of techniques you might want to try to minimize for sort of optimization. Actually, I asked AI to write some code. So if the code is wrong, I do apologize. I haven't checked it thoroughly. I think it's okay, but please let me know if it's wrong. But the general ideas, I didn't talk about some of them. You've got things like minimizing the amount of data that you're storing on chain, and this is because the S store. If we, where are we? The S store opcode is very expensive. I mean, it's saying 100 here, but that's just a kind of the starting value. There's details here of how much it could work out to be. So reducing the amount that you're storing on chain is going to be a good idea. So what you can do is, if you can get things into smaller variables, that means you can pack more variables into one storage slot, which means rather than having multiple store opcodes, or store operations happening, you can reduce those by doing one store operation with multiple variables all going into the same slot. The drawback is that then when you're trying to use those variables, you have to pull all of them out of the slot and then do some masking to get the one you want. And so there's extra computation, extra gas being used to do that. So may not be beneficial, but it could be. Other things here: avoiding redundant computations. So using things like pure functions if you can. That's going to make more sense. But the next one's the same sort of thing. This it's about packing also. There. So this is the is that the one? No, that's yeah. Yes, sorry, that's just packing again. Writing in assembly does make sense. It's still, you can still make optimizations yourself better than the optimizer sometimes. So it does make sense to it can make sense to use assembly. So some inline assembly there. If you were on the Advanced Solidity Bootcamp, that's you're going to know all about that. Understanding about memory and call data. So this example, use call data is cheaper, so use that wherever you can. The only point of using memory is if you're then going to need to update the items. But if you don't, which is usually the case, then use call data. It's going to be cheaper. Minimize the number of external contract calls. It has a cost to do that. I mean, we saw the wherever it was, we had the call, didn't we? Let's go back to that. If I can find it. Oh. Okay, the call. This potentially can also be a minimum gas of 100. You have to put lots. You have to do lots to put on the stack. So that could be expensive as well. The only thing, but it can make sense if you are calling to a library, because that means that somebody else has deployed that bytecode that you're going to use. So it's more expensive runtime, but then it's cheaper because you don't have to deploy something. So you have to decide which makes more sense to you for that. Short circuiting. This is the point about where is it? Oh, this one. This is the point that you when you're calling functions, you can use Boolean logic to make sure that you don't call expensive functions if you don't have to. So that's what that's about. And then the final bit is about the create to opcode, so that allows you to deploy a contract to a specific address, which can be useful. All right. So moving on. What's next? Okay. I didn't go through this one. So let's have a look at this. So this. I think maybe this was actually first in the article. So this is a more general one. I won't go through. Well, we could actually have a quick look, but this is just. I think this is just showing you how function selectors work. If I can, is this going to? Oh no. Okay, I can't work. Yeah, somewhere I've got something out of. Oh, because I've got these things here. Anyway, But the point is that um, it's yeah, it's jumping depending on various values of function selector. So the the EVM can jump to the correct point in your code. What he talks about here is this is I can't copy this because it's in the wrong format, but this is the um, getting the function selector from the call data. So in the call data, in the thing that you receive from the transaction, the first 4 bytes of that are going to be the function selector. So let me show you. Um, Wherever that is, call data load. Yeah, so this gives you the call data, and you can have an offset for that. So you can say where you want to start in the call data. So that's what that is doing. Wrong one. Let me close that. And this is doing a shift to shift that. I think this is shifting to take out the function selector there. Yeah, I'm not sure. I can't. Yeah, I can't run these because they've got these bits involved. But anyway, this is just talking about how function selectors work. But what he's saying here is to do this in a different way and do this with a single byte. In fact, we can try this one. See if we can follow this one through. Not going to. No. Okay. Oh, I'm not sure what the values I need for these. Okay, I can't run that, but anyway, so it's a way of masking masking that the way that works, or making a more optimized version. And this idea of a jump table, if you haven't come across this before, it's if you write in huff, then you use jump tables. So that's what that's about. It's a way that we can say where we're jumping to in the bytecode and set that up in a more optimized way and a more readable way. Okay, I'm gonna have to skip that because I can't really show this. Okay, but you can have a read through that. The next bit. Yeah, so what I really wanted to finish with is looking at ways, if you're writing at a very low level, if you're writing huff, or you're looking at some bytecode, how can you try to optimize what's happening on the stack, which is not always. I think there's quite a skill to uh, doing that. I mean, this really is, yeah. If you're writing huff, this is really what you need to be able to work out what to do. Um, oh, yeah, David got to go. Okay. Yeah, if you're writing huff, you need to know what to do. And the stack management is quite a skill, and so much so that the compiler and the optimizer haven't quite got there yet, because we've got the error that you sometimes get, this stack too deep error. That's really where the compiler has written some bytecode but kind of got it wrong, and it ended up trying to get something from too low down in the stack. You can only reference items, reference the first 16 items on the stack, and the compiler has tried to do something beyond that, which then has thrown in error. So so stack management is not easy. These are some ideas of how you can optimize some of that. so this first example is about comparing addresses to something. So you're pushing. So yeah, push 20 should be familiar to you now. You're pushing an address, and then you're testing whether that's equal, and then doing it again and again. Um, this one is this is a more efficient way of doing it by using this, because in this one you're introducing the same address 3 times, and checking it against whatever it is. But with this one, what you do is put it on the stack, then duplicate it, and then do swapping to swap. Excuse me, to swap with some other values that you're comparing it with. And yeah, so you don't have to do the push 20 again. If I don't know, I can look at the cost. Okay, so push 20 is a minimum of 3 gas. Oh, maybe it's only going to take 3 gas. Okay, but it's not. Still, yeah, it's. I think in this case the problem is more that we end up doing more opcodes generally. So yeah, this one's more of a better approach. Really, this is the same thing. The using swap to swap around the arguments. And yeah, this is really the same thing again. Actually, using, because this is using dupe here to keep something on the stack. So this is a similar one, and I tried. I had an example which was, it was trying to do this kind of thing. Actually, I'm not sure whether this one works. Let me just try this out. But what I was trying to get an example together that would. Let's try this. Okay, it doesn't error, I don't think, but I'm not sure it's doing quite what I want it to do. The idea, what I was trying to get to, was to um have to add 5 to 7 and to add 6 to 7, but do that in an efficient way without repeatedly putting 7 onto the stack, because it's a common thing that you're adding. So you can do that with dupe and swap. So I'll leave that if you want to try it out and work out how to do that. I started to do it, and then yeah, I didn't finish it. But I think it's a case that when you're doing it, you need to, you can push the 7. You need to do a dupe. You then you can do the problem is that when you do an add, this will take items. Yeah, so you do the dupe, because when you do the add, that's going to take the original items off the stack, so your 7 would disappear. So if you do a push of 7 and a dupe, then that means you'll have 7 on the stack twice, which is what you want, because otherwise it would disappear. But then you need to do some swapping as well, because you're going to need to get rid of the result that you had earlier on. So you do need to do a little bit more manipulation as well. And where all this came from, there's a nice article here about, well, it's about the EVM generally, and about working with the stack. Yeah, it has a lot of the ideas that I was presenting. Okay, that's everything I wanted to say, really. As I say, it was mainly about, I wanted to have a look at some of these articles, and go through some of the techniques, and to show you how they actually work in bytecode, because I thought that would be interesting for you. And I put a little bit of information about MEV generally, and arbitrage bots as well, because that's probably kind of where you may want to be using this, although it doesn't have to be. But certainly if you find that your transactions are being front run by some generic front running bot, then these type of techniques could help. But there are other options as well. You could use different protocols. You could use something like some middleware like flashbots, etc. Yeah, there are other options, but I think these are very interesting techniques. This guy, he writes some very interesting articles. Yeah, really knows his stuff. So yeah, subscribe to his articles as well. And read what he has to say. It'll make you a good developer. Really help your Solidity development if you do that. Anyway, that's pretty much all I wanted to present to you today. I'm happy to hang around a bit if you have questions or you want to chat about stuff. But yeah, that's pretty much it. Thanks everyone for coming.